Hooray. So we're going to sketch derivatives. And I hope you've got pencil and paper ready, kids. At home. What are you? How come you're laughing like that? Makes me uncomfortable. Okay. Ah, there we go. Here's what I want to do. I'm going to show you the original function. And it's a piecewise function. And what I want you to do is I want you to sketch the derivative. So, oh, can I do that? Oh, maybe I don't want to do that. Oh, there's the derivative as well as the what you would have sketched for the derivative. Okay, so I don't know what I'm doing after all. I'm going to stop doing that.
Nailed it.
Okay, screen share. Okay, so I guess I want to do this. And actually, the other option would be a lot better. Good. Okay. Put that over there. Okay, there we go. So I'm going to undo. No, wait. I'm going to undo that. Okay. So I'm going to draw a curve. See the function in blue?
Mm-hmm.
I want you to sketch what you think the derivative of that function will look like. So just a quick sketch, the main regions, and then hold it up to the camera. And I'm going to pick somebody. So you guys can see my screen, right?
Yeah.
It's going to look funky.
Where's the curve?
Not going to be like a nice smooth thing.
Yeah, I know.
The drawing they actually give you is a little bit wrong.
Yeah, I'm thinking that too.
Meg, I can see you on the internet. You're looking over at RJ's. RJ thinks he's got it.
Oh, you want me to do it too? I
Hey,
don't know.
RJ's not doing it. Let's see what Meg's looks like here. I'm gonna do this. And you think it looks like that?
I have no idea. But because the slope's constant going up and the slope's constant going down, but I know how to plot it.
Okay. Well, let's take a look.
Oh,
Big round of applause.
so you do attach it.
You shouldn't.
Put it wrong.
What you drew is correct.
Oh.
Yeah. Like what you drew is really correct because as you can see, so I'm going to grab the cursor here. You can see that this function is not, the derivative doesn't exist there, even though it's continuous. The derivative does not exist at those cusps. And so really down where they're showing, down here where they're showing these little connections, that shouldn't happen. So what you drew is correct. It's not differentiable at those positions. That's really good. Okay. However, it is kind of a neat tool. Okay, so I'm going to undo that. And, oh, I know what to do next. I'm going to take this, and so it's called tilt. And tip it up like that. So it goes on forever, and this time, I want you to sketch the derivative.
This is like the functions in new, right?
Yep.
Oh, okay, let's do this.
And oh, RJ's got his up, and RJ.
Sorry, I'm really shaky right now.
Oh, that looks good. So RJ says it's like a horizontal line, positive, and that's what Meg says too. And it's a horizontal line, and it's positive. Big round of applause, everybody.
Right? It's not a horizontal line.
It's not?
No, whatever.
I
Oh, it
I'll
was.
take it.
It's exponential.
I can throw an exponential one, but whatevs.
Okay, all right. Anyway, well,
That sounds like,
yeah.
like
So the derivative, that's like y equals, it's something like y equals 2x right there. So when you take the derivative of y equals 2x, you're going to get
Oh, yeah.
y equals 2, right? So, yeah, we just think about it in terms of the power rule. Okay, so I'm going to zero everything. And I'm going to, let's see, we've had cusp, we've had that. This one's kind of interesting. Oh. Okay. All right. This now is funkier. So this has nice smooth. What are you thinking? You think you got it? You think you got something?
Can you do that? I can't tell.
You are frozen in my thing.
Oh,
Just a second. Oh, there we go. There's Megan's, and let's take a look at RJ's. Ooh, RJ's is pretty funky.
where's it?
You can
I
look at
can't
this.
see
You can't see.
I was like, I can't see it.
Okay, so let's go over this. Okay, everybody, right here, right there, the slope is 0. So your derivative should be 0 somewhere in the middle. In this interval here, how would you describe the derivative? Is it positive or negative?
Positive.
It's positive through there. And what about in this region beyond that local maximum?
Negative.
Okay, now let's look at this region from the axis over to the maximum. It's positive, and how would you describe the slope through to about here? Positive and
Increasing.
increasing. And from here to the maximum,
Decreasing.
it's positive and decreasing. Yeah. And here we are at the maximum. How would you describe the slope in this region?
Negative. Increasing.
Negative and getting more negative, right? And what about in this region? From here on.
Negative and decreasing.
Negative and decreasing. So let's take a look at what the... So there it is. Okay?
It goes with mine, so don't worry.
Yeah. So yeah, actually, you picked up some of the main features there, RJ, where you
It was
noticed
changing, yeah.
you noticed where the 0 was, so that's an obvious point.
And then how it changed, that's why I tried to.
Yeah, so there's the intervals where the slope is positive and above the line, and then there's the places where the slope is positive and the derivative is below the line. And then, yeah, picking up those intervals where the slope is increasing but positive and then decreasing but positive, that's pretty good. It changes at a point of inflection. So it goes from being positive and increasing to being positive and decreasing. We call that a point of inflection. We actually call it concave up and concave down. Okay, let me give you a new one. So this is a GeoGebra one. There we go. So, so that's a cubic equation. There's a bit of a giveaway there. But think about the things like where the slope is going to be 0, for example. And that tells you kind of a point you can sketch in there.
there it is.
So both of you guys have another cubic one? Is that right? Like another
Yeah.
SC sort of cubic one?
Yeah.
Okay. And so you've got 2 zeros, RJ. You've got it being negative up until the 0, and then,
What?
oh, sorry, it's positive to begin with.
Yeah, I was gonna say what?
Positive to begin with. Okay, so your derivative should be above the line in the positive region.
Oh, right, right.
Yeah, where the slope is
Oh,
positive.
yeah.
Okay, and I see Meg's got hers is positive. Okay,
I think I just have mine upside down.
Yeah, I think you do. Or just behind it.
and then Meg, you've got it at 0 there, and then the slope becomes negative and decreasing to point of inflection.
Mhm.
Okay, all right. So I know where yours is coming from now, Meg. Oh my goodness! I hope there's no stalkers that saw me do that.
What?
I put your image on instead of your parabola.
Oh, no.
Okay. RJ, do you have a revised version?
Wait, is it going?
Almost looks like a parabola, RJ. Okay. Well, let's take a look at the derivative. So this is GeoGebra, and like GeoGebra will just do your derivatives for you. Like it's a little bit like Wolfram Alpha. It almost will do your homework for you. Okay, ready, RJ?
Yeah.
There it is.
Alright.
Oh. Oh, excellent.
Yeah, so it makes sense. First of all, that's a cubic function, so the derivative is going to be a parabola.
Hmm.
So, Meg, you had
I just did.
the 0. Yeah,
put the
that's
wrong
right.
spot.
Yeah, you had your derivative sort of drift off like this. But this slope, as we move from left to right, it comes from being like infinite and positive, being 0. Then it switches to being negative. Then it goes back to 0. Then it heads back towards being infinite and positive. Okay, so it doesn't hurt. You can just grab some points and you can say, right, the slope of the function is 0 at that crest, and so there's the point where it's going to cross that axis. 0 here, it's going to cross the axis here. It's negative in between, and so the derivative is going to be negative, and it's positive from negative infinity to this point that's like negative 2.5. And so your derivative is going to be above the axis. And it's also positive from this point, which is about negative 1/2, onwards to positive infinity. Okay. That seemed pretty straightforward? Great. That's it.